Have you ever been driving down a highway, maybe just cruising along, and wondered, how is this even here? Well, that seemingly simple ribbon of asphalt you travel on every single day is an absolute marvel of engineering. It's this whole system of hidden complexities, all governed by an incredibly detailed rulebook. And today, we're going to crack that book open. So here's our road trip for today. We'll start with the billion-dollar question of why a road even gets built in the first place. Then we'll decode its fundamental design. After that, we'll see how engineers tame a road's biggest enemy, rain, and we'll explore the surprisingly complex layers hiding right under your tires. And finally, we'll see how these massive structures can actually coexist with the natural world. All right, first up, the billion-dollar question. And it's a big one. Before a single shovel ever touches the ground, a massive financial and really a societal question has to be answered. Why are we even doing this?
Yeah, this isn't just about, pouring some concrete and calling it a day. Building a highway is a monumental public investment, and it demands an absolutely airtight justification. You can't just build one because it seems like a good idea. You've got to prove it's necessary.
And that proof, it comes from following a very, very specific rulebook. In Korea, it's called the Korean Design Standard, or KDS. Think of it like the literal source code for every single road. It lays out the bare minimum requirements for everything, from safety to efficiency. And it's what engineers turn to answer that huge initial question. So to justify a new road, engineers basically have to become fortune tellers. And they do it with this really rigorous four-step process. First, they predict future growth, more people, more cars. Then they map out where all those people are going to need to go. From there, they actually model what transportation choices people will probably make. And finally, they calculate exactly how all that predicted traffic will flow onto the brand new road they want to build. Once they have all that traffic data, they run the numbers. The key test, the big one, is the benefit to cost ratio, or BC ratio. It boils down to this really simple but super powerful idea. Do the benefits to society, like all the time we save not sitting in traffic, outweigh the massive cost of construction? It's basically the gatekeeper that prevents our tax money from being wasted on a bad idea. This number right here is the magic number. For a project to even get off the ground, its benefit to cost ratio must be greater than 1.0. This is the ultimate green light. It's the official stamp of approval that says, yes, this road will provide more value to people than it costs us to build. Okay, so the project gets the green light. Now the real fun begins, the design work. This is where engineers use a very specific language of design choices that basically define what kind of road this is going to be and what job it's supposed to do. So the very first thing they do is decide, what is this road's job? An arterial road, like a highway, has one main goal: high-speed mobility. Get people from point A to point B fast. A local road, on the other hand, has the opposite job, giving you direct access to your driveway or a local shop, and collector roads are the links in between that. Well, collect all that traffic. This classification is the single most important decision. And that one choice, it dictates everything else, especially something called the design speed. A highway out in the flat countryside is designed for 120 kilometers per hour. A local road in the city? Maybe 50. And this isn't just a suggestion for a speed limit. It's baked into the very geometry of the road, the curves, the hills, the width of the lanes, all to create a super safe and predictable environment for you to drive in. And get this, it gets incredibly specific. I mean, all those major arterial roads, those big highways, they're basically designed around one key vehicle, the semi-trailer. Its length, its weight, its turning radius, all of that dictates the gentle curves and wide lanes you see on every major highway. The entire system is built to make sure the biggest things out there can use it safely. Okay, on to our third section. We've talked cost, we've talked speed. Now let's talk about a road's greatest, most persistent enemy: water. Seriously, you might not see it, but every modern road is basically a sophisticated defense system designed to fight a never-ending battle with rain. And trust me, the stakes are super high. If you let water run wild, it will destroy everything. It seeps into the ground and turns the foundation into mush. It carves away the slopes on the side of the road. It gets into tiny cracks in the pavement, freezes, expands, and boom, that's how you get potholes. And of course, it pulls on the surface and can cause terrible accidents. So what do engineers do? They build this incredible circulatory system to get water away from the road fast. You've got surface drainage, like gutters, to clear the lanes you drive on. Slope drainage protects the embankments. You even have underground pipes acting like veins, lowering the water table. And transverse drainage, like culverts, are the big arteries, moving huge amounts of water from one side of the road to the other. So you might be wondering, how on earth do they know how big to make all these pipes and channels? Well, it's not a guess, it's math. But it's actually a pretty elegant little formula called the rational method. They can predict the peak amount of water they'll have to deal with by factoring in how spongy the ground is, how hard it's likely to rain, and how big the area is that's draining to that one spot. It's a surprisingly simple way to predict a very chaotic event. But here's the thing. They can't design every single pipe for a once-in-a-century apocalypse storm, right? That would be crazy expensive. Instead, they design for a specific frequency. A simple gutter on the side of the road might be designed to handle a 10-year storm, but a massive culvert running under a mountain highway, that thing has to be ready to handle a 50-year storm, a much, much rarer and more intense downpour. All right, section 4. We've tackled the money, the speed, and the water. Now let's talk about weight. That simple surface we drive on every day, it's not so simple. It's actually a complex, multi-layered structure that's been engineered to withstand the crushing force of millions of vehicles year after year. Okay, so a typical asphalt road, think of it like a layer cake. For real. The top layer, the surface course, is what we see. It's smooth and durable, but the real magic happens underneath. The base and sub-base courses are these thick layers of crushed stone that take the super concentrated load from a truck's tire and spread it out over a huge area, so the natural ground underneath, the subgrade, can handle it without turning to mush. Now, concrete roads, they play by a whole different set of rules. Instead of that flexible, layered system, they rely on a single, thick, and incredibly strong slab of concrete. This rigid slab doesn't just spread the load, it's so strong it can actually bridge over little imperfections in the ground beneath it. It's like a solid plate versus a stack of mats. So the big question is, why pick one over the other? Well, like with most things in engineering, it's all about trade-offs. Asphalt is more flexible, and it's generally quieter to drive on. Concrete is super rigid and can be way more durable, especially under the constant pounding of heavy trucks. That's why you often see it on major, heavy-duty highways. The choice really depends on traffic, climate, and of course, the budget. Okay, for our final section, let's zoom way out. Because building a road isn't just about physics and finance. It's about putting a massive piece of man-made infrastructure right into a living, breathing ecosystem. So the final challenge is making sure that road can coexist with the world around it, instead of just destroying it. You see, modern road design isn't just about cars anymore. The rulebook explicitly says engineers have to think about the environment. This means building things like wildlife bridges and underpasses so animals can cross safely. It means putting up massive noise barriers to protect people who live nearby. It means fences to keep deer off the highway, and even special filters to clean all the oily runoff from the road before it gets into local rivers. I mean, check out this quote directly from the design standard. It says that if a drainage culvert is in an area with a lot of wildlife, you should design it so that animals can easily walk through it. This is just a fantastic example of this new way of thinking. A simple pipe for water can also be a safe passage for wildlife. How cool is that? So, here's my challenge to you. The next time you're on a long drive, take a second to really look at the road. Look at the gentle slope of the shoulder that's whisking away the rain, the wide, sweeping curve designed for a truck you might not even see. And maybe, if you're lucky, you'll spot a wildlife bridge arching over the lanes. It all leaves us with a pretty big question to chew on. How do we keep building roads that connect all of us without disconnecting nature in the process?